Hello class, today we'll be covering Chapter 2 of Mechanics of Solids, which is strain. There's only two sections in this chapter. First is the deformation of a material, and second is how we measure that deformation in engineering terms, which is strain. Deformation refers to the change in shape or size of a body. In this class, we will primarily consider linear elastic deformations. Deformations are a linear function of the applied loads or stresses, and the deformations are generally not permanent, and the materials will return to their original size and shape after the loads are removed. There are two primary types of strain: normal strain, which measures the change in length per unit length of a line within a body, usually normal to some plane, and shear strain, which measures the change in angle between two lines that are originally perpendicular to each other, usually also measured within some plane. For this class, we will consider strains that are very small, or close to zero, and much less than 1. In this diagram, we see a body with 2 points, A and B, in an undeformed and a deformed shape. Delta S describes the length of the distance between A and B of the undeformed body, and delta S prime describes the distance between A prime and B prime of the deformed body. We can calculate the average normal strain along the line by subtracting the original length of the line delta S from the new length of the line of the deformed body, delta S prime, divided by the original length of the line, delta S. The strain at a point along this line can then be defined as B approaches A, or as the length of delta S approaches 0. In the planar member as shown here, we can describe the strain along the x and y axis of the rectangle. Strain along the x-axis is defined as the change in length along the x-axis divided by the length along the x-axis. For the strain in y, we have the change in length along the y-axis divided by the original length in the y-axis. Using this convention, a positive strain is always defined by increasing length, and a negative strain is always defined by a decreasing length. And so we have adjusted the equations to match this convention. Since the angle of the sides of the rectangle have not changed, the shear strain on this diagram is 0. Shear strain is defined as the measure of the change in shape of an object. To define shear strain, we must have two lines that are originally orthogonal or at 90 degrees to each other. Here in the diagram, we have the undeformed body and two lines defined by the points A, B, and C. In the undeformed body, the angle between the lines A and B and A and C is 90 degrees, or pi over 2. In the deformed body, we've defined the angle between A prime, B prime, and C prime as theta prime. The shear strain is defined as pi over 2 minus the angle theta prime. The shear strain at a point is defined as the lengths of the lines go to 0, or as B and C approach A. Shear strain can be described using degrees or radians, since it's a measure of angle. However, the use of radians is much more common. In the planar diagram, we can define the shear strain relative to the x and y axes by taking the inverse tangent of the length A divided by the length Ly. If we make the small angle assumption, this is equal to A over Ly. In this diagram, the normal strain along the x and y axis is 0, since the lengths along these axes isn't changing. Since the shear strain is just a measure of the change in angle, this shear strain is equal to this shear strain, where the angle is divided up into two angles relative to the x and y axes, and this shear strain, where we're just measuring the angle relative to the x-axis. In all of these examples, the area of the rectangle hasn't changed. For engineering materials, the shear strain and strains are normally very small, or much less than 1. This allows us to make some simplifying assumptions. Primarily, we can make the small angle assumptions. This allows us to assume that tangent of theta is approximately theta, sine of theta is approximately theta, cosine of theta is approximately 1, theta is approximately equal to C divided by B. Theta is also equal to, or approximately, A divided by B, and C is approximately A. In this slide, we can see graphs of the sine of theta, tangent of theta, and cosine of theta. From this we can see that for angles very near 0, sine of theta is equal to theta, tangent of theta is equal to theta, and cosine of theta is equal to 1. These graphs give us an idea of the accuracy of the small angle assumption as a function of the strains and shear strains. Thank you for watching this review of engineering strain. Next time, we will discuss the mechanical properties of materials.